Good day, Dr. Almond and Dr. Yvonne. I'm Jack, and together with Karen, Jaden, and Marylou, we would like to present our sustainability project titled Solar Hydrogen Powered Microgrid. This is the table of contents for the presentation. Let's start with the introduction. The selected location is Long Pila Village, a remote village in Sarawak with strong solar energy potential, with solar irradiance ranging from around 2.15 to 7.351 kilowatt-hour per meter square per day. This project proposed an off-grid rural electrification system by integrating renewable energy and energy storage technologies. The system is designed to provide stable, sustainable, and clean energy supply for remote communities. For the problem statement of this project, Long Pila Village currently receives electricity through the SARS project, but the electricity supply is limited. Each household only receives approximately 1 kilowatt power capacity and around 3 kilowatt hour daily energy allocation, which is only sufficient for lighting and basic appliances. In addition, the village still relies on the diesel generators as backup power sources, which is a non-renewable resource. This leads to high transportation costs due to the remote location, while also contributing to carbon emission and environmental degradation. Therefore, a more reliable and sustainable energy solution is needed for rural electrification. This project proposed by aiming to achieve several key objectives. The main objective is to provide reliable and sufficient electricity supply for the village by increasing the household energy capacity from 3 kilowatt-hour to 6 kilowatt-hour daily. Additional power is also allocated for schools and clinics with 10 kilowatt-hour and 20 kilowatt-hour daily, respectively. The second objective is to develop a fully off-grid renewable energy village by integrating solar PV system, battery storage system, and also the hydrogen storage technologies. The third objective is to support the integration of emerging hydrogen energy technologies, which acts as the long-term energy storage for the village. The fourth objective is to reduce the reliance on diesel generator by minimizing fossil fuel usage and reducing fuel transportation costs. And the final objective is to reduce carbon emissions, improve environmental quality, and also support the sustainable development. The proposed system consists of three main subsystems. And firstly, the solar PV system acts as the primary energy harvester and is integrated with MPPT controller to maximize the power extraction. And the second BESS system provides short-term energy storage during nighttime or low solar irradiance conditions with using the lithium-ion batteries. Meanwhile, the hydrogen system provides long-term energy storage and backup power supply, which consists of electrolyzer and fuel cell technologies. Let's move on to the technical specification part. The total required power is calculated based on household, school, and clinic loads, and after considering peak sun hours and system losses, the required PV power is about 435 kilowatts. The DC bus voltage is selected as 340 volts based on the 230 volt AC supply requirement of Malaysia. The REC 380 volt solar panel is selected for the PV system, and a total of 1,140 panels are used with a 6 series and 190 parallel configuration. The battery bank capacity is calculated to be approximately 8,800 ampere hour, and therefore 88 lithium-ion batteries rated at 100 ampere hour are selected. For the hydrogen subsystem, a PEM electrolyzer and PEM fuel cell are selected, and the electrolyzer power is calculated to be around 462 kilowatts. The hydrogen storage system is designed for 7 days of backup energy. Approximately 460 kilograms of hydrogen are required, with a storage volume of around 16 cubic meters. Lastly, this table summarizes the overall technical specifications of the proposed microgrid system.
This is the system block diagram. All subsystems are connected through a DC bus. Electricity will be supplied to load through inverter. A monitoring dashboard is developed to monitor the system state, such as power flow and bus voltage. This is our simulating model. The hydrogen storage system will be separated due to software limitation. It is assumed to be connected to the battery, which absorb or supply power through battery. The system input will be solar irradiance. It is the primary energy source for the PV generation system. The output requirement refers to the load demand, where the system is required to supply sufficient power to the load. A daily profile of solar irradiance ranging from 0 to 1800 watt per meter squared is generated as input. The simulation time is set to 24 seconds, with 1 second represent 1 hour, to shorten the simulation time while maintain a meaningful result. Due to limitation in obtaining the actual load profile of Long Pila village, with this calculation, an average load of 50 kW is simulated.
This is the overall simulation for the hydrogen energy storage system. It is consisted of two main components, which are the electrolyzer and a fuel cell stack. They are working together with some other subsystems.
This is the system input, solar irradiance daily profile, and this is the 50 kilowatt average load. Now we run the simulation. The system response can be obtained through the scopes. This is the response of solar PV system. Overall, the response matches the pattern of solar irradiance. Looking at the solar panel's output voltage, there are some spikes. This is the transient response due to the interaction between boost converter and the DC bus. Oscillations are also observed, especially for the output current. Hence, in real-life implementation, circuit limiter can be implemented to prevent the oscillating current from damaging the components. For the output power, it is correlated to the output current. Next, for BSS, overall, it is able to maintain the DC bus at a set point of 340 volt. However, there are oscillations. This is due to the oscillations occur in the battery current. A battery control is implemented to match the reference current by adjusting the duty cycle of bidirectional DC-DC converter. As you can see, since both graphs are overlapping, the battery current can match the reference. Therefore, the main cause is the unstable reference current, suggesting better PI controller tuning is needed to produce a more stable reference. In addition, the sign change of battery current indicates charging or discharging action. This is correlated to the battery state of charge. Before 7 a.m. or after 7 p.m., the battery will discharge, and vice versa. And the load side, 50 Hz AC can be produced, but the voltage peak is slightly distorted, and the RMS measure is not fully stable, so better components parameter refinement is needed. This is the overall power flow. The power of solar PV system and BSS look symmetrical. This means that the system is working well, where BSS will absorb the excess power or supply power when needed. Looking at the power balance, ideally it should stay at 0, so there is no excess power or insufficient power delivered. This pattern is matching with the DC bus voltage, which depends on the BSS response. BSS is limited to absorb maximum power while maintain the DC bus voltage. Also, it requires time to response. Although we treat the simulation time 24 seconds as 24 hours, the internal simulation battery response is still 24 seconds. So the transient response is more obvious in this case. Nevertheless, the trend of power balance towards zero is observed, means that the load demand can be supplied continuously. An unexpected power drop is observed when solar irradiance reaching maximum. As a filter is applied when measuring the power, oscillating components are filtered, with the lower part remain, and we will see it as a drop.
This is the overall simulation result for the hydrogen storage system. Firstly, for the hydrogen production rate, it is increasing consistently around 366 liters per minute. For the fuel cell current voltage and power, we can see that there is a sharp increase in the beginning, but actually if we zoom in, they are increasing slowly as the hydrogen in the beginning of simulation will start from zero, slowly increase and contributes to this phenomena. Later, we also visualize small increment, which is the hydrogen field slowly increase until it reaches the maximum.
In short, the simulating model developed can meet the project objectives to supply reliable and stable off-grid electricity to Longpila village.
So to analyze the performance of our system, we developed a monitoring dashboard using Microsoft Power BI. The data comes from MATLAB simulation and is exported into CSV files, which are then imported into Power BI for visualization. The dashboard provides a global view of microgrid operation by showing how energy is produced, stored, and distributed throughout the system. First, the solar horizons and PV power graphs illustrate the availability of solar energy and the electricity generated by the photovoltaic panels. Then, the battery SOC and power flow graphs show that charging and discharging phases, highlighting the battery's role in balancing energy production and consumption. The dashboard also includes hydrogen-related indicators, which allow us to monitor hydrogen production and the operation of the long-term storage system. In addition, DC bus voltage and power balance graphs help verify the electrical stability of the microgrid. Finally, several KPIs summarize the overall system performance, such as average irradiance, maximum PV power, total hydrogen production, and energy surplus or deficit. To obtain this indicator, we use DAX function in Power BI. As you can see in the example, specific formula and comments must be created to calculate the different values automatically from the simulation data. These KPIs provide a quick and quantitative assessment of the efficiency and reliability of the system. Overall, the dashboard provides a clear and structured overview of the microgrid's performance and helps validate the energy management strategy implemented in the project. As a future improvement, real-time monitoring could be implemented to display live data directly in Power BI. However, this will require more complex connection between the simulation and the database or APL. It could make the system even more interactive and realistic. To assess the feasibility of implementing solar hydrogen system in rural Sarawak, a PEST analysis was conducted to examine the main external factors influencing the project. First, the political will. So the Sarawak government strongly supports the rural electrification and renewable energy development, but most households are connected to electricity. Some remote communities still lack access to the grid. National initiatives such as MyRER and NETR also encourage the development of renewable energy and hydrogen technologies, creating like a favorable environment for the project. From an economic perspective, many remote villages still rely on expensive diesel generators. In addition, geopolitical tension and conflict in Middle East can increase the fuel price volatility. Solar hydrogen system could therefore provide greater energy independence and more stable long-term costs despite their high initial investments. Reliable electricity will like improve education, healthcare, and economic activities in the rural communities. Since many villages already use solar technologies through previous electrification projects, acceptance of renewable energy is generally positive. However, some concerns remain regarding the hydrogen safety and public awareness. The project relies on proven technologies such as solar panel, batteries, electrolyzer, hydrogen storage, and fuel cells. These technologies make the system suitable for isolated areas. Nevertheless, challenges such as energy losses, hydrogen storage, and maintenance requirements still exist. Overall, the PES analysis shows that strong political support, clear social benefits, and mature technologies make solar hydrogen system a promising solution for rural electrification in Sarawak, despite some economic and technical challenges. So, while the PEST analysis focused on the external environment, the SWOT analysis evaluates the project's strengths, weaknesses, opportunities, and threats. One of the main strengths is that the project is aligned with government strategies promoting renewable energy in Sarawak and Malaysia. It addresses the real needs by providing reliable electricity to remote communities, and the combination of solar energy and hydrogen storage also gives the project an innovative and sustainable image. However, the project requires a high initial investment, especially because of the cost of hydrogen technologies and the challenge of working in remote areas. As a new company, it may also depend on subsidies and external expertise during the early stage. There is a growing demand for rural electrification and clean energy in Malaysia. Government support and funding programs could facilitate the development. In addition, becoming a pioneer in a hydrogen-based microgrid could provide a competitive advantage and opportunities for the expansions in South Asia. But on the other hand, the company would face competition from cheaper solar battery systems, the fluctuation in the price of materials and possible regulatory change would increase the costs. Public concern about hydrogen safety may also slow adoption. Overall, the SWOT analysis shows strong growth potential thanks to government support and increasing demand for renewable energy. However, financial challenges, competition, and public acceptance will be key factors for the project's success.
We also conducted risk analysis for our project in 7 aspects. Firstly is the financial risk. As we are using renewable energy, the initial capital cost and the hydrogen production costs are actually quite high. The cost estimation for our project can be found in the appendix. Next, the technical risk is talking about the components that we are using like solar panels, electrolyzer, fuel cell, battery system, etc. They will degrade slowly over time. The operational risk is related to the load profile and the load demand, which is actually changing all the time in real life. Solar has intermittent nature, which means it can be blocked by the clouds and rain, so it is not a very stable energy. Safety risk is one of our major concerns as we are using hydrogen and it is highly flammable and it can be explosive. Furthermore, environmental and site risk occurs as we need land required for the solar and hydrogen installation, and improper disposal can lead to land pollution. In addition, maintenance and reliability risks is also considered as the system performance will degrade faster if lack of maintenance. Lastly is the social and community acceptance risk. As hydrogen is still an emerging technology, community engagement and user education are required for proper usage of the system. We have found out the risk level of each risk using the probability vs impact matrix, and the highest risk level is actually the operational risk. However, one significant thing is we give the mitigation priority to operational risk and also safety risk for the highest priority, as safety is always the first priority that we must handle for the project. Our project has achieved the Sustainable Development Goals 7, 11, and 13. As we are using solar and hydrogen energy, we are able to reduce the dependence on fossil fuels and also reduce the carbon as well as greenhouse gas emissions. We also successfully provide reliable and stable continuous electricity for the villages in Long Pila village. The members and responsibilities in our team. We have Jake, who actually focus on background and site study, and he is in charge of the solar PV system part. Next, we have Jaden, who actually did the component costing research and estimation. He in charge of the hydrogen storage system part. Karen and Marylou in our team. Karen mainly focused on research on existing solution, BESS construction and simulation, and she helps to do the risk analysis of the project. For Marylou, she helps to design the monitoring dashboard and also did the pest and SWOT analysis. Some future improvements that we can make for our project. First, energy management system which we can add on to improve the power distribution, accurate modeling and load variation which we can simulate more accurate result which is close to the real life implementation in future, improve system response, also add on hydrogen leakage detection for safety purpose, and lastly simulating module development as there are some simulating limitations for our project right now. In conclusion, our project has successfully simulated a solar hydrogen powered microgrid system that can provide a reliable and sustainable off-grid electric supply for Long Pila village. Our system is able to supply sufficient and also continuous power during both day and night time, as we are having hydrogen subsystem which effectively used as the long-term backup energy storage. One shining point of our project is that it is capable to eliminate the dependence on diesel generators, therefore carbon emissions can be reduced. Towards the end, all the objectives of our projects are achieved. That's all from us. Thank you very much.